So this session we are going to continue the current electricity part, theory part 2. The first one what we are going to discuss is effect of temperature. So effect of temperature on resistivity and resistance. Yes. As we said, the fractional change in resistance, that is directly proportional to change in temperature or is proportional to or that is equal to alpha into delta theta or delta T, where delta theta is a temperature change and alpha is a coefficient of thermal resistivity. Okay. So this is the proportionality constant, temperature coefficient of resistivity. This will be constant. Or the same expression can be written as delta R is nothing but R final minus R initial. That is equal to just cross multiply R initial alpha into delta theta. Or from this I can write that RF is equal to R initial plus R initial alpha into theta. So this is the S. So this is the modified form of the original definition, Ri into 1 plus alpha into delta theta. So this is the required expression for temperature. This is let us consider the two temperature range theta final minus theta initial. At the temperature theta 2, some books they may use 2 and 1. That is our convenience about the usage of symbol. So therefore theta final corresponding resistance is R final, and theta initial temperature, the corresponding resistance is R initial. So similarly the same expression is true for in the case of resistivity also. The fractional change in resistivity is equal to alpha into delta theta. As we said, the same manner I can write that rho final is equal to rho initial into 1 plus alpha into delta theta. So this is the variation of resistance and resistivity with respect to temperature. Yes. Now there are three graphs which will study the important for your examination point of view. So temperature versus resistivity versus temperature graph, and here material can be classified as three category. One is pure metals. So this is for metal, and this is for alloys. This is for alloys, and this is for insulators or semiconductors that we will discuss in 14th chapter, semiconductor. So I am taken temperature in Kelvin scale, and here also when you draw the graph, kindly make the units properly, represent the units along the axis. So rho in ohm meter, yes, and here also rho in ohm meter, and here also rho in ohm meter. So in the case of conductor, pure conductor or metals, the graph will be slightly non-linear. In the case of alloy material, the graph will be a linear straight line. But in the case of insulator, the graph will be a rectangular hyperbola. Yes. So this is the graphical representation between resistivity and temperature for metals, alloys and insulating materials. We know that in the previous session we derived the expression for resistivity, rho is equal to m divided by Ne square tau. So here there are two variables, number density and relaxation times are the variable with respect to temperature. So what is the variation of tau with respect to temperature means? So tau is inversely proportional to temperature. So therefore as the temperature increases, the tau value will be decreases. But in the case of n, so how the n will be, number density will be vary means, so when n is proportional to temperature, generally when temperature increases, number density of the material also will increases, but there are some negligence when compared to the variation of tau that we are going to discuss now. Yes, there are certain alloys material. From this the same expression we can get that alpha is equal to, so alpha is equal to R final minus R initial divided by R initial into delta theta. This alpha can take any sign, either positive or negative. So in the case of metals, pure metals, alpha will be positive and a high value. In the case of alloy material, like constantan, manganese, as nichrome, like that of alloy material, alpha value is positive but less. This is more and this will be less when compared to these two. And next, in the case of insulators or semiconductors, the alpha will be negative. So that means the alpha negative means as the temperature increases, the alpha value will be decreases. So that is the thing, negative temperature coefficient of resistivity. Now you please see that there are some reasoning questions related to this. First reasoning question is why alpha is positive for alloys and metals. So alloys and metals. So this is one of the reasoning questions. So for that we can give the explanation with respect to this. But in alloy or metals, the number density, the change in N with respect to temperature is negligible. So I can write, so because of that reason I can write the dependence of resistivity with the variable parameters as 1 by tau. Yes, as temperature increases, tau will decrease. So therefore, as temperature increases, tau will decreases, therefore rho will increases. When rho increases, it will get alpha has to be positive value. And for the second question, so why that the semiconductor or insulators are having a negative temperature coefficient of resistance or resistivity means, in this case, so why alpha is negative for insulators or semiconductors. Here you just see that there we said that the change in N value with respect to temperature is negligible, and here in case of insulator or semiconductor, the change in tau is negligible. So therefore the dependence can be written as inversely proportional to number density. As temperature increases, as we said here, as temperature increases, N also will increases, therefore rho will decrease. So that's why the alpha value for insulator or semiconductor materials will be negative. And this is one of the important reasoning question. And they will ask why we are alloy materials are preferable to make the wire resistance means their alpha value is less positive, or their change in resistivity by a considerable amount of change in temperature is negligible. So because of that reason, alloys are suitable for making wire resistance. So this is the explanation about the effect of temperature on resistivity and resistance. Next we are going to discuss another topic. That one is resistor combinations. So another very important one. So resistor combinations. Okay. This is very important for any kind of circuit based discussion. So please listen carefully. Yes. Okay. So now this one will be series combination, and this will be as a parallel combination. Here I will give a little bit explanation because this is basic for a cells combination. So in series combination of resistance, I is same but V will be different. And in parallel combination, I will be different. So I will be different and V will be same. So this is the main thing what we have to be keep in mind. So now we draw the diagram for a better understanding. So therefore two resistance are considered here. End to end connection is generally called a series, and this ladder type is called a parallel connection. Yes. So let us consider I be the current. So this is I2 and this is I1 and this will be R1, R2. And similarly the same current is entering through all these resistors. Say this is R1 and R2, corresponding potential is V1 and this has to be V2. Yes. Which one is different? You just add that value. Okay. So now you see that the total value or the total voltage or effective voltage. So V is equal to V total is equal to V1 plus V2. So similarly here I can write that total current I is equal to I1 plus I2. So parallelly when you are doing, we can easily identify what kind of difference is there. So now we see that according to Ohm's law, V is equal to IR. So I into R net, because this is the total voltage. Total voltage is nothing but total current and total resistance. This effective or total or equivalent resistance I can take, that has to be RS, since it is in series combination. Therefore I can write that I into R1 plus I into R2, or RS is equal to R1 plus R2. So this is the required expression in the case of series combination. Now you please see that here the same story. So just recall your Ohm's law, V is equal to IR or I is equal to V by R. This is a simple expression. Therefore this is the total current, therefore total voltage by total resistance. Total voltage by total resistance, that is equal to V by R1 plus V by R2. Or I can write that 1 by Rp, that is equal to 1 by R1 plus 1 by R2. From this I can write that R parallel equal to R1 R2 divided by R1 plus R2. So this is the a general expression. We can extend this formula for any numbers up to n numbers. Suppose all are equal. So suppose all the resistance are equal, then what we can do means, if all R values, all resistance are equal, then we can say that are equal or same, then we can write that R plus R up to n numbers. Therefore Rs is equal to n times of R. Therefore the total resistance in series combination is always greater than the individual resistance in the given circuit. But here the same story for the equal resistors. I can write that Rp is equal to R by n. So since n is greater than 1, therefore we can say that Rp is lesser than the individual resistance in the circuit. So individual resistance in the circuit. So R individual. So that is the thing we keep in mind. So how to find out voltages? So we know that. So V1, that is equal to I into R1. So I is nothing but total voltage, total current. So I is nothing but total current equal total voltage by total resistance. Total voltage by total resistance into R1. Therefore V1 is equal to V into Rs is nothing but R1 plus R2. So here we can write that. Therefore R1 by R1 plus R2. So this is the general expression for V1. So instead of finding the current value, by knowing the total voltage and resistance, we can calculate that. So similarly we can write V2 also, V into R2 by R1 plus R2. So this is the another expression. The same manner we can discuss here also. So here we have to find out the individual current value. So therefore current I1 is equal to V total, V total divided by R1, because V is same here. So the voltage remains the same across this parallel resistance network. So therefore you just see that. So 1 by R1, this V is nothing but I into R net, because total voltage is equal to total current into total resistance. Therefore I can write that I into 1 by R1 into Rp is there, you just substitute over there. So R1 R2 divided by R1 plus R2. So this gets cancelled out. Therefore I can write that I1 is equal to I into R2 by R1 plus R2. So similarly we can write that I2. So we can write that I2. So I2 is equal to I into total current into R1 by R1 plus R2. So now you just see that analogy between or comparison between them. So V1 means same resistance by sum of resistance. I1 means opposite resistance. I1 means opposite resistance. I1 is equal to total current I into opposite resistance by total resistance. So this is the easiest way to calculate current in each branches or voltage in across the each resistors. So this is the basic thing we must know that, because for further discussion the topic called cells and the combination of cells. This should be very, very important. Kindly note down the content, students. The next what we are going to discuss is cells basics and the combination of cells. That is very important as a concept for your theory discussion. Okay, even for MCQ. In plus 2 point of view, there is no additional information between CBSE and MCQ part. Therefore, this is enough for your MCQ part also. So now we are going to discuss what is a cell. Yes, we know that to make the current flow, we must apply some potential difference. So a cell is nothing but a device which produces the potential difference, or which makes the, very simple, we can say that it is source of EMF or potential electric potential differences. So let us consider generally a cell consists of two main part. One is called electrolyte and another one is called electrodes. So this is the say positive electrode and negative electrode, and this is electrolyte. Any salt solution are suitable as chemical solutions. Now please see that whenever these ends are connected by means of wire or any material, conducting material, the current, as we said earlier, current always going from positive terminal to negative terminal in the external circuit. In the external circuit, current will go from positive to negative, but inside the cell it is going from negative electrode to positive electrode. That you please keep in mind. Generally, the electrical circuit symbol for the cell can be given as it will be like this. The positive, the lengthy line represents the positive terminal is a higher potential when compared to negative electrode. So this is internal resistance. Or the same can be represents, or the same can be represent. It will be like this. So E comma R. What is that E? What is that R? We are going to discuss now. Yes. Now first you see that the first parameter related to the cell is the first one is EMF. If there is no current flow, that means when the circuit is open, you just see that. So when the circuit is open, there is no current flow in the circuit. At that time, what is the maximum potential difference measured by the voltmeter? This is the cell arrangement. This dotted rectangle represents the cell arrangement E and R. The potential difference across the electrodes of the cell when there is no flow of current, that is I has to be 0, then the corresponding potential difference is nothing but yes, EMF, the maximum potential difference across the yes, electrodes of the cell when there is no current flow in the circuit, and that is called yes, EMF. The unit is volt only. So the second part is terminal voltage. The second one is terminal voltage V. So this case what will happen means the circuit is closed, so therefore there is a flow of current in the circuit, and the circuit is closed one, and there is a external resistance R. So some current will flow from positive of the battery to negative of the battery. In this case what we are measuring across the a given resistance or across the terminals of the cell, that is called a terminal voltage. So we can write the terminal voltage equation for two cases. This circuit, if you are getting this current from the battery or cell, that is called a discharging circuit. That is called a discharging circuit. If you are given the car battery and all, you know that sometimes we can use the charging process. We are sending the current to the battery or cell, that is called charging process. If you are getting the current or current from the cell, that is called a discharging process. So for a discharging process, the expression for a terminal voltage is given by V is equal to E minus IR. So for a charging process, the terminal voltage is E plus IR. That means during the charging process, the current will go from positive to negative of the electrode. So since the current direction changes during the charging process, that's why this minus becomes to positive sign. So from this, these are the two important relation is what we need for the further discussion. Now the third parameter, so that is called the internal resistance. Internal resistance. So just to see that the internal resistance, because the resistance offered by the electrolyte of the liquid or electrolyte of the cell is generally called internal resistance. So from this equation I can write that the expression for R is equal to, just take that is, so E minus V divided by what will be there, I will be there. So in the same manner here also we can write the another expression, what is the voltage across this external resistance, that can be written as V is equal to IR. So if you are using this I as to be V by R, then the same expression can be written as E minus V divided by V into R, or the same can be written as just cancelled out E by V minus 1 into capital R. So there are two expressions for internal resistance. One is this one and another one is this is the internal resistance expression. This equation will be used in potentiometer, so just to keep in mind. Now next one is so the fourth one is a current delivered by the cell. So during the discharging circuit, what is the amount of current delivered by the cell? That is a current delivered by the cell. Current delivered by the cell, I is equal to, generally you can consider E net by R net. This is the very general expression. Since here we are using only one cell or cell of EMF E, therefore I can write that I is equal to E divided by R net. We know that these two resistance are in series, therefore R plus R. So this is the general expression for current delivered by the cell during the discharging process. So if that external resistance R external equal to R has to be 0, if you can, because we cannot make a small or internal resistance has to be 0, we cannot make it as to be 0. So for that reason we can say that the external resistance is 0. That means we are directly connect this as a circuit, then we can get that the I maximum is equal to E by small r. So this is the maximum current delivered by the cell when there is no external resistance in the circuit. And the next one is the fifth parameter. What we are going to discuss is a graphical study or some important graphs. Okay, yes. So what are the graph? Here the variables are voltage, resistance, and that current will be there. So therefore the first graph what we are going to draw is a voltage versus current I. Just to take this terminal voltage expression, V is equal to E minus IR, or V is equal to minus R into I plus E. Just modify this equation. Now this equation is very similar to the equation of as a straight line. Since y-axis I am taking V, therefore y is equal to M. Along the x-axis I has to be taken plus C. Since the y-axis intercept is positive, so this intercept value will be E. So negative slope, because the slope is nothing but what is that? Or you can say that modulus of slope is nothing but internal resistance. Therefore the graph will be like this. So this is the graph terminal voltage versus current. And the second graph is, this is the first graph is over. The second graph what we are going to discuss is another one. So voltage, yes. So voltage versus external resistance. Before going to that, we know the formula V is equal to IR here. Therefore I can write that V is equal to IR, that is I is nothing but E by R plus R. So therefore R into E divided by R plus R. So I just take R outside and cancelled out. Therefore I can get E divided by 1 plus small r by capital R. So this is the required expression to draw this graph. Now you please see the graph. Yes. So this is external resistance and this is the terminal voltage. Yes. So when external resistance has to be 0, then this becomes to infinity. Therefore 1 by infinity has to be 0. So therefore when R has to be 0, there is no terminal voltage across this. But when R increases, the graph will be increases as shown in the figure. When R tends to infinity, 1 by infinity is 0. Therefore V is equal to E. And this is the maximum voltage, terminal voltage, that is nothing but EMF of the cell. So that is the of terminal voltage versus external resistance. And the third one what we are going to discuss is third one is EMF versus external resistance. So we said that here. So what is EMF means? The potential drop across the terminals of the cell when there is no current flow. That means the circuit is open, means these resistance are not included. So these resistance are not included here. Therefore I can say that the graph between external resistance and EMF is independent value. Therefore the graph will be a straight line with the zero slope. So therefore, and this is the graphical study for voltage versus R and voltage versus current and EMF versus R. And the fifth parameter we can, sixth parameter one is generally for any DC source, DC current, since so far we are discussing only DC current only, the power P is equal to VI, that is equal to I square R, or that is equal to V square by R. So this is the electrical power when we are using DC current. So this expression we must know for the further discussion. Now based on this extension of the theory part is a very important 3 or 5 mark category. Combination of the cells. So combination of the cells. Combinations of cells. So since we are already discussed resistor combination, this discussion is very easy to deal. Yes. So as we said earlier, I can go with series and parallel combination. This is a series and that will be a parallel combination. So this is parallel combination. As we said earlier, the same thing only. So here I will be same, V will be different, terminal voltage will be different. But here, I will be different, and V will be same. So this is the general expression what we get, or conditions what we get. Now we can discuss this one very elaborately for the understanding of the concept. Let us consider there are two cells which are connected in a proper way. Proper way means one positive is connected with another one negative, like that it should be connected end to end and successive manner, plus minus. This is E1 R1, this is E2 R2. It delivers some current I. So we know that current is always coming out from the positive terminal during the discharging process. As we said in the resistance part, here also we can say that here the voltage, terminal voltages are different. So this is V1, V2. The equivalent cell or the cell which will deliver the same amount of that is called E series or equivalent EMF and equivalent resistance, which will deliver the same current. So that is called equivalent cell. So the same expression what we are going to discuss. Since V is different here, therefore total voltage is nothing but V1 plus V2. We know that what is expression for V here for discharging circuit, E minus IR. So since it is a total voltage, therefore E total, that is E series, because I am talking about series, E series minus I into R series, because current is same here. So that is equal to, for V1 we can write that E1 minus I into R1 plus E2 I can write that E2 minus I into R2. You just group the as terms. So that is E1 plus E2 minus I is common, R1 plus R2. So just compare the as dimensions of the quantity on either side, then we can say that yes, the E net or E series, that is equal to E1 plus E2. If n number of cells are there, we can add n numbers. Similarly, R series is nothing but R net. R net is equal to R series, that is nothing but R1 plus R2. Yes. So if all are same, yes, another condition, if all the cells are identical, cells are same or identical, say for example n numbers are taken, then we can say that ES is equal to N into E and RS is equal to N into R. This is the expression what we get. Yes, this is the another result. And what is the current delivered by this arrangement is, you just see that I is equal to, as we said earlier, I is generally nothing but E net by R net. Therefore here E net is nothing but ES divided by R net. This is NE divided by R net is nothing but external resistance. As we said here, you just see that this is R and this is a small r. So total resistance is external resistance plus internal resistance. So similarly here external resistance plus the total internal resistance is NR. So this is the current delivered in the case of a series combination of the cell, I series. So what is the condition to get the maximum current? As we said here, when external resistance is 0, current will be maximum. Similarly here you just see that the R net, if this term has to be 0, RS, that is NR equal to 0, if the total resistance is 0, that means we cannot 0 exactly, but this can be negligible. So this can be negligible, because as we said earlier, we cannot make 0 internal resistance, but when compared to this I can neglect that. So therefore R is very greater than R net, that is equal to NR. If this condition is valid, then in summation that can be, this term can be omitted. Therefore I can say that I maximum, that is equal to NE divided by capital R. So this is the condition for as maximum current delivered in the series combination of the cell. Suppose, as we said, what is the proper connection between connection of the series combination of the cell means one positive and negative should be alternatively connected. Instead of that, suppose similar polarities are connected in this manner, positive and negative to negative and positive, like that. Say this is E1, this is E2 and R1, R2. In this case, what is they say? Assume that E1 is greater than E2. So this cell is having a negative EMF. You just reverse the sign of the EMF when the polarities are wrongly connected. Therefore, in this case, I can write that E net is equal to E1 minus E2. Why I am putting a minus for E2 only means since E1 is greater than E2. Suppose E2 is greater, then you can write E2 minus E1. So we can implement the or reverse the sign which one is wrongly connected and whose value is less when compared to the another cell. Okay, but there is no change in a resistance value, because whether it is properly or wrongly connected, resistance value will be remains the same. So this is the detailed theory about your series combination of the cell. The same analogy can be extended for yes, parallel combination also. So now you please see that, yes, this is the, yeah, so the given cell. So E1 R1 and this is E2 R2. So the internal resistances. Let I be the current enter in this. So this is I1, this will be I2. How much current is coming out from the positive? The same current is entering here also. So just to keep in mind. So as we said here, V is same. In a parallel combination, V will be same. So for that reason, the different term, that is I net or I, that is equal to I1 plus I2. So this is the expression or result what we have to find, similar to here. Before that, you try to understand from the terminal voltage equation. So V is equal to E minus IR. Yes. So from this, I is equal to what? So E minus V divided by R. So E minus V by R, the same can be written as, written as, that has to be, yeah. So this is the important expression what we have. Or the same can be written as here, I can write this one here. So therefore I is equal to E by R minus V by R. This is the current equation in terms of terminal, from the terminal voltage equation. So I can take this expression, I can use this here. So therefore the total current, is nothing but sum of individual current. The total current is nothing but E total by R total minus V by R total, because V is same here. Yes. Therefore E total is nothing but E parallel minus so by R is nothing but R total. Here R total is nothing but RP, total internal resistance, minus V by RP. Similarly for I1, I can write that first cell, therefore E1 by R1 minus V by R1 plus E2 by R2 minus V by R2. Just to rearrange the terms, so E terms are together and V terms are together. So 1 by R1 plus 1 by R2. So as we said earlier, compare the dimensions of same quantity on either side. So in the place of E by RP, this term is there. In the place of 1 by RP, this term is there. So therefore I can say that E net or E parallel is by R parallel. So that is given by the total resistance is, or EMF value is given like this: E1 by R1 plus E2 by R2. And another one is, this is the important results what we get. Similarly 1 by R parallel, that is equal to 1 by R1 plus 1 by R2. As we said earlier, R1 R2 divided by R1 plus R2. The same expression can be written as, instead of doing this type of calculation, I can write E parallel, that is equal to RP. So RP into, just cross multiply by E1 R2 plus E2 R1 divided by R1 R2. Yes. So RP by R1 R2 is nothing but 1 by R1 plus R2. You just see that, or you take this RP and substitute over there. So we can get that, so just see that RP, substitute here, we can get that EP is equal to RP is nothing but R1 R2. So this R1 R2 and this R1 R2 I can write for your better understanding. So E1 R2 plus E2 R1 divided by R1 R2. So these terms gets cancelled out. Therefore the another expression for E without the RP value, we can write that EP, that is equal to E1 R2 plus E2 R1 divided by R1 plus R2. This is the another expression for your parallel combinations. So as we said earlier, if all are same, the cells are identical, we can say that E net will be, this is very important results which will differ from the series combination. E parallel is equal to E itself, but R parallel is equal to R by N. R parallel equal to R by N. Yes. So this is the important results. Whatever may be the identical cell, we used, say for example, M number of cells to avoid the confusion of the indices. So that is R by M. M number of identical cells are used. So here whatever may be the identical cell, we are getting the same EMF. Yes, that is very important point. As we said here, the current delivered IP is equal to E net by R net. So E net by R net, that is E net is nothing but E itself divided by R net is nothing but external plus internal. Yes, therefore external resistance plus internal resistance RP value. And again the same condition. What is the condition for maximum current? So if you just see that, if this as we said here, the external resistance is greater than the total internal resistance, you just reverse the condition here. So the external resistance is smaller than the total internal resistance R by M, then this R can be neglected. This R can be neglected. Therefore we can write that, so therefore I max. So I max, that is equal to, this term is gone, then this M will go to numerator. Therefore ME divided by small r. So this is the condition for I max, and this is the corresponding maximum current, students. So this is the complete theory about a series combination of the cell. So this is very important thing, because there are many MCQ or as well as CBSE questions are there. Please kindly note down the theory, student.